So we're going to start off Unit 4 with some definitions. Um, Chemical reaction, I think you all know, but here's what the formal definition is. What we're going to talk about in this video is how chemical reactions are not creating or destroying anything. All that's happening is that stuff is being rearranged. So that's really the key to a chemical reaction. You also need to have different substances. Reactants or reagent, usually you'll hear reactants. Those are the things you start with. Products are the things you form. And then a precipitate is just a special form of product that is in the solid state. All right, and we'll talk about that because precipitates are really what chemists are often looking for because they're trying to create something, they're trying to synthesize something, and that something is the precipitate, which they then isolate. So here's an example of a chemical reaction. So I'm just going to label some things on here. The reactants are everything before the arrow. The products are everything after the arrow. The arrow itself, you would usually say gives, reacts to form, something like that. Forms, anything like that. These numbers right here are subscripts, and you're familiar with those. We've been using those in our formulas. The bigger numbers, this one, and then also this one, but I won't bother labeling them both, are coefficients. And that's going to be really important when we start balancing later in this video. The other things in the parentheses are states of matter. And you'll have your normal solid, liquid, gas, but you'll also often see AQ. AQ stands for aqueous, which just means it's a solution, and water is the solvent. So a lot of times you'll see that with ionic compounds, like for example NaCl. NaCl is solid, table salt, but if you put it in water, it dissociates, it dissolves, and so we would often put AQ in order to get it to react. So when you see AQ, that's a solution. There are 5 types of chemical reactions that we're going to go over in this class. So what I'm going to do is give you an example of these and kind of explain what they look like. And then towards the end of that, we'll start actually classifying different reactions. These are paired, like synthesis and decomposition are related to each other. Single and double replacement are related to each other. And then combustion is just kind of a weirdo on its own. So synthesis, the formal definition is when 2 or more reactants combine to form a single product. Our general reaction would be something like this. This is just variables where you have 2 reactants, and they form one product. They combine. So the key here is going to be 2 or more reactants and one product. And then down here is just an actual example of one so you can kind of see what it looks like. Decomposition is the opposite. We're going to have one reactant that breaks up into 2 or more products. So you'll see that it's really just the opposite. We have AB as our reactant, and then it splits up into A and B. And here is an example of what one of those would look like. Single replacement reactions. What's going to happen is that the anion switches from one cation to the other cation. Our general reaction looks like this, where we still have A and B, but the thing doing the switching, the X, is the anion. It goes from B to A. So this is what one of those would look like, okay? You can see our anion, remember that's just a negative ion, switches. It goes from Ag, it's attached to Ag, and then it is attached to copper. And you might notice that here there's two, and here there's just one, okay? We're going to get to that in just a minute, but that's because of the charge. So the charge on silver was 1. So when it's crisscrossed, you just got 1 NO3. The charge on copper was 2, okay? Again, we'll talk about that in just a minute. The way I'm going to have you tell the difference between single and double replacement is you can definitely look at this and see what's going on. An easier way is to label them, and by them I mean the reactants, as either elements or compounds, okay? So if you have 2 products and 2 reactants, if you have an element and a compound, it's single replacement. So if you see here, this is an element because it has 1 capital letter. This one has multiple capital letters, so it's a compound. And it doesn't matter what order they would be in. If it was compound plus element, it would still be single replacement. But if we go to double replacement, we're going to have an X switching from A to B. And then we also have a Y switching from B to A. So if you look here, we have OH going from Na to Cu. And then we have Cl going from Cu to Na. So they are switching partners. You also can see that both reactants have more than 1 capital letter, so they are both compounds. So if you have a compound plus a compound, you get double replacement. And that's going to come in handy in just a few minutes when we start classifying these reactions. The last one we need to talk about is combustion. Combustion is its own little thing. It's actually meant to be easier to recognize, but for some reason, sometimes students really do have a hard time. So what's going to happen is a hydrocarbon combines with oxygen to form CO2 and H2O. A hydrocarbon is just something that has hydrogen and carbon. So when you look at our generic form, okay, we're always going to have C and H, and they'll have different subscripts. So the X and Y are the subscripts here. You'll notice that the only thing that can change in this entire generic reaction is the X and Y. Everything else is set. So we have CH hydrocarbon. It's always going to be O2, okay, oxygen's diatomic. And your products are always going to be CO2 and H2O. So here's an example of what one of them is, okay? There's a bunch of different ways to recognize this. If you have a hydrocarbon and O2, it's combustion, okay? If you don't realize that, if you look at the products and it's CO2 and H2O, it's combustion. So what I tell students to do is look for O2 by itself as a reactant, so before the arrow. All right, so if you have both of those things, chances are you have combustion. There are some where that's not the case. There's a very specific synthesis one that's not the case, but chances are you have. Take a look at the rest of it. Do you also have a hydrocarbon, CO2, H2O? Make sure that you have that stuff. So now let's take a look at some examples. So what you should do first when you're doing these examples is count the number of reactants and products you have. Because if you don't have 2 and 2, then you know it's either synthesis or decomposition, because the other 3 have 2 and 2. So here we have 2 reactants, but only 1 product. 1 product, there's only 1 reaction that has that, and that is synthesis. Now the second one, you have 2 reactants and 2 products. So when you have 2 and 2, that's what I mean by 2 and 2, 2 reactants, 2 products. When you have 2 and 2, you need to do a little bit more work. So do we have O2 by itself as a reactant? We do not. We have oxygen, but it's O3 and it's connected to Ag and NO, so it's not by itself. So now we know it's either single or double replacement, and to tell the difference between those, we look for capital letters. This is a compound, and this is also a compound, so we know this is double replacement. Now, if you've taken science in another country or somewhere else, you might hear double displacement. It's the same thing. Single displacement and double displacement are the same. All right, so that's it for classifying reactions. As you can see, that's pretty easy. So we'll do some practice on that as well in class. But that's not really enough for this first lesson. So we're going to also move on to balancing. So we have a third law. Remember in the last unit, we learned multiple proportions and definite proportions. Now we have the law of conservation of mass. This is a very important law. This law tells you that matter cannot be created or destroyed. What will happen is that things will rearrange to form new products. But you will not have all of a sudden extra carbon, or you will not lose nitrogen when you have a reaction, something like that, okay? You will have exactly the same mass before and after the arrow, and you will have exactly the same amount of atoms and the same amount of moles. Okay, so what this law tells us is that we have to balance our chemical equations. We have to make sure that's true, that we have the same amount on both sides. So coefficients and subscripts in a reaction are going to represent moles, and you have to have the same number of moles of each element on both sides of the chemical equation. Okay, now to do that, you change the coefficients. You cannot change the formulas, the subscripts. Remember, you already wrote formulas. You know that that comes from the charges of the atoms, right? You know that those subscripts are crisscross, they come from the charges. You cannot change them. Remember when we first started writing formulas, we said you have to have a certain amount of aluminum to go with chloride, right? You have to keep that the same. That doesn't change. So the only thing you can change in a chemical reaction is a coefficient. So what I'm going to have you do is when you first start, draw boxes around the chemical formula so you can know and you remember to never change anything. That's going to be the first thing to go here. Once you get practice with this, you're not going to do that very often. Then you can make an element inventory and you change the coefficients on the reaction so that the before matches the after. Let's do a couple so that makes a little bit more sense. So the first thing I'm going to do is put boxes around my chemical formulas, so I know not to touch anything in there. And then your element inventory will look something like this, a nice little chart. And I listed all of the elements, and then before is going to mean before the arrow, and after is going to mean after the arrow. So right now, I'm just going to write how many I have, okay? And that's going to come from the subscripts. So for Na, I have 1. For Cl, I have 1. Be, I have 1. And then F, I have 2 before the arrow. After the arrow, Na, I have 1. F, I have 1. Be, 1. And Cl, 2. So now what you're doing with the work here is getting these two columns to match each other. Okay, then we will know we have the same amount of each atom on both sides. The trick is that you can only change coefficients. So watch what happens. I notice that Cl is not balanced here. These two numbers are not the same, okay? So what I will do, and all you're allowed to do is multiply, what I would do is, okay, I need to multiply this by 2 to make them match, right? So I find the Cl before the arrow, it's right here, and I change its coefficient to 2. The problem is I can't touch anything inside the boxes. So I can't change the subscript. That doesn't work. I also can't put a 2 in the middle of the formula. We've never seen that before, and we've been using formulas for a while. That doesn't work either. What I can do is put a 2 right here. Okay, that changes Cl to 2. But that 2 doesn't just apply to Cl, it also applies to Na. So as soon as you change one, if they're in a compound, you're changing everything. So now Na becomes a 2. And now my NAs aren't balanced, okay? And it doesn't matter what order you do it in. I'll give you some tricks on the next one, but if you wanted to go to F, that's fine too. So now my NAs aren't balanced, so I need to multiply this by 2. So I go and find my Na after the arrow, and I put a 2 in front of it. That 2 changes Na, but it also changes F. What's great is that that's exactly what I wanted. So now the columns match each other. Na has 2 in both, Cl has 2 in both, Be has 1 in both, and F has 2 in both. Okay? Now all the elements don't need to have the same amount, like Be and F can be different. That's totally fine, as long as they're the same before and after the arrow. One thing I would keep in mind is that sometimes students get very bogged down about the charts and making them match and forget to put the coefficients in the actual reaction. So their chart is nice and pretty, but their reaction is still unbalanced. The chart is just a tool to help you balance the equation. I actually don't care about the chart, and I don't require that you show me any work when you balance. So if you can do this without the chart, which many of you will get there by the time we're done with this, you're welcome to do that. All I care about is seeing this done correctly. So let's try another one. I'm going to put the boxes. Oh, whoops. And I'm going to write H2O right here to make it a little bit easier. It came down here. We'll get rid of that. All right. So same thing. I'm going to go and write how many I have before the arrow and after the arrow. So Na, there's 1. O, there's 1 here and 4 here. Okay, so 1 plus 4. H, same thing. There's 1 here and 2 here. So we'll do 1 plus 2. And then S, we have 1. After we have 2, 1, 5, 2. All right, so I said on the last one that you can go in any order you want, and that's still true. But I will say, for something that shows up more than once on one side, save that for the end. So for H, see how it's not balanced, but here it's in two places before the arrow. Save it for the end. Oftentimes they'll work out themselves, and if not, it's much easier to do at the end for different reasons. Um, but oftentimes they'll just work out when you do the other ones. So let's take a look. So the other thing that's not balanced here is sodium. So let's do sodium. Sodium is a 2 after the arrow and a 1 before. So I'm going to put a 2 right here. So that changes this to 2. But it also changes oxygen and hydrogen. And a very common mistake that students will do is they'll go here and they'll be like, oh, I'm going to multiply this by 2 and it's going to be 6. And I'm going to multiply this by 2 and it's going to be 10. But that's not true, okay? You're not doing the multiplication in the chart. The chart is to help you keep track of how many elements you have, okay? That's all it's there for. You're not doing any work. So instead, you go up here. This 2 applies to Na. It applies to oxygen here. So now we have 2 oxygens here, but we still only have 4 here. We didn't change that. We didn't put a coefficient here. So it's 2 plus 4. So that's going to be 6. And then for hydrogen, it's 2 plus 2, because we didn't change this. So that will be 4. So now, the only thing that's not balanced is oxygen and hydrogen. Okay, they both show up more than once on one side, but oxygen does that a lot more. So I'm going to do hydrogen first. So hydrogen has 4 here and 2 here. And what's nice is that it's only one side, it's only once after the arrow. So if I put a 2 there, that changes to 4. And then oxygens, I have 2 here now, but still just 4 here. So 2 plus 4 is 6. And now we are balanced. And that's it for balancing. That's the whole trick. So what we'll do is just practice, because that is the whole thing. But then obviously the more difficult reactions you have, the more difficult it will actually get. But there's no more rules or anything else to learn about balancing. So now it's just all about practice.